Assalamu alaikum warahmatullahi wabarakatuh. In this video, inshallah, I'll try to solve some examples from textbook, chapter 7, final control element. So this is the valve, the flow control valve, and we introduce the different parts of the control valve. We have the equations that control the valve. First equation we need to introduce is the flow with respect to the velocity. So Q is equal to A V, where Q is the flow in meter cubed per second. V is the velocity of the fluid, which is in meter per second, and here the area of the bulb area, which is in meter squared. So this is the first equation relating the flow with the velocity of fluid. Let's solve first example that use this equation. We have example 7.6. Okay. Example 7.6. In this example, alcohol is pumped through a pipe of 10 centimeters diameter. So the diameter of the pipe is 10 centimeter. The velocity is equal to 2 meters per second. Find the volume flow rate, the volume or volumetric flow rate. So we have the equation, which is Q equal to A times V. Q is the volumetric flow and V is the velocity of fluid, as I said. So we need to first find the area. The area is equal to, because it is a circular pipe, it is pi d square over 4, because d here is the diameter. So this is equal to pi 10 centimeter, which is 10 to the power minus 2, because it is in centimeter and it is square. We divide it by 4. This is equal to, when you calculate it, this will be equal to 7.85 times 10 to the power minus 3 meter squared. Once we have calculated the area, then the flow is equal to A, the area, which is 7.85 times 10 to the power minus 3 meter squared, times the velocity, which is 2 meter per second. So meter squared times meter will be meter cubed, and here per second, this is per second. So when we multiply this by this, it will be 0.0157 meter cubed per second. So this is the first example. Now we have another formula that governs the flow control valve. Okay, we have the volumetric flow here. This is the first equation. We have another equation, which is Q equal to K. Q is equal to K times the square root of delta B. And this is a general equation that governs the flow or relate the flow, volumetric flow, with the differential pressure across the valve. Because the valve here, inside the valve, there is this is a restriction, and according to Bernoulli equation, since we have a restriction like orifice plate, for example, then there will be the flow in this case will be proportional to the square root of the differential pressure between the upstream and downstream. So here the pressure is B1 and here the pressure is B2. So the delta B in this case, this is B2 and this is B1. So delta B in this case is equal to B2 minus B1. Okay, and usually the units here in this equation is we use in this equation the SI system of units. Okay, so let's in this case the K here is the proportionality constant, and it has unit K, it has a unit of meter cubed per second per Pascal, the unit of pressure in SI system, to the power 1/2. So this is the unit of the proportionality constant K. Delta B, the unit of delta B is the Pascal in this case, Pascal. So let's solve an example that use this equation. Okay, this equation, which is example 7.7. Example 7.7. Okay, in this example, a pressure difference of 1.1 psi, so delta B is 1.1 psi, occurs across a constriction in a 5 centimeters diameter. So D is 5 centimeter pipe. The constriction constant is K is equal to 0.009 meter cube per second per kilopascal to the power 1/2. So it is the square root of kilopascal. Find A, the flow rate in meter cubed. So we need Q. Okay, then we need to find the velocity. So first we need to calculate Q. Delta B, because it is in PSI, we need to convert it to, this is PSI, we need to convert it to kilopascal, so we have to multiply it by 6.895 kilopascal per PSI. For 1 PSI, each PSI equal to 6.895 kilopascal. So we have 1.1, then we have to multiply with this conversion factor, and the result will be 7.5845 kilopascal. This is the differential pressure. Then Q is equal to K square root of delta B. So in this case, this is equal to 0.009, this is K, the constant K, times square root of 7.5845 square root to the power half, and this is equal to 0.025 meter cubed per second. This is the Q. This is the flow, volumetric flow in the pipe or in the control valve. Now we need to also calculate the velocity. Then we need to use this equation, Q equal to A times V. So V is equal in this case Q over A. Okay, so we need to calculate A, or we can just divide Q by A, which is by D square over 4, and this is equal to we have 4 here, we can make it up, so we have 4 times Q over by D square. We substitute in this equation, so we have 4 times Q, which is 0.025. We already calculate Q here, so it is this is meter cubed per second. We divide it by times d square, which is 5 times 10 to the power minus 2, because it is in centimeter, the diameter here, squared. Then if we calculate this, the velocity then is equal to 12.7 meter per second. Okay, this is the second this is the second example. Okay, now we have this control valve here. Again, this is control valve complete with the actuator, and here the signal comes from the controller. It is for usually to 20 milliamps. Okay, and this converter converts the current to pressure from 3 to 15 psi, which is standard, industry standard, and then the pressure here convert to force applied to this diaphragm, which is fitted from these two bonds. This is the diaphragm. Okay, and this is a normally open control valve, because it is normally open. When we apply here current, then the pressure here apply force, then this system, this is the stem, and this is the plug. Okay, and this is the seat, and this is the valve body. So here okay, this is normally open. When we apply pressure from the top here, it will close the control valve. So it is normally open, or we can say it is air. We apply air pressure to close, because it is normally open. We can say this or this equivalently. Okay, now so it is air to close or normally open. We have this curve, okay, and we already explained the different type of control valve: the quick opening, the linear, and the equal percentage. And the equal percentage is very important in control applications, because it gives equal percentage of flow according to the same change or equal change in the stem position. Okay, in the stem position here. So let's solve an example, which is example 7.8, regarding the quick opening. So it is example 7.8. Okay. We have in this example an equal percentage valve, has a maximum flow of Q maximum here is equal to 50 meter cubed per second. Okay, and a minimum of 2 meter cubed. So Q minimum is equal to 2 meter cubed per second. If the full travel is max is equal to 3 centimeter, find the flow. We need the flow at S equal to 1 centimeter. These are the given information, and we need to calculate the flow at S equal 1 centimeter. We know for equal percentage valve, Q is equal to Q minimum times R to the power S over S max. R, which is the rangeability, R is the rangeability. R is called the rangeability. and is equal to R is equal to Q max over Q minimum, and it has unitless, it is unitless quantity. It doesn't have unit because we divide flow by flow. So in this case we have 50 meter cubed per second. Q minimum is 2 meter cubed per second. So meter cubed per second divided by meters will be cancelled. 50 by 2 is equal to 25. So R is equal to 25. Then Q is equal to Q minimum, which is 2 meter cubed per second. This is Q minimum, times R, which is 25, to the power S. We need to calculate Q at S equal 1 centimeter. So this is 1 centimeter. This is S over S max, which is 3 centimeters. So centimeter will cancel with the centimeter. So this is equal to 2 times 25 to the power 13. Okay, and this is equal to 5.85 meter cubed per second. Okay, so this is the flow. Okay, and we can see if we need to calculate here at 0 centimeter, the flow was Q minimum, which is 2 meter cubed per second. When the stem is at 1 centimeter, we calculate it to be 5.85 meter per second. At 2 centimeter, you can calculate it, it is around 17 meter cubed per second. At 3 centimeters, which is the maximum, the Q in this case is 50 meter per second. Okay, so we have this range. So you can notice that if we go by 1 centimeter each time in the stem position, we increase the stem position each time by 1 centimeter, same change, then we have the flow will have a triple. Is a triple. So the 2 times 3 is around 6. 6 around 3 times 3 around 17. 17 times 3 is around 50. Because this ratio actually around 2.9. It's not 3 exactly. We multiply it by 2.9. So this is equal percentage in this case. Okay. Then we have also the last thing we need to consider here is the control valve sizing. The control valve sizing, the most important factor in control valve sizing is the value or the constant or the factor which is called CV. What is the CV? The CV actually is the number of US gallons, okay, per minute. Okay, this is the flow. That flow through a fully open valve with the pressure difference of 1 pound per square inch, 1 psi. Delta B is equal to 1 psi. So again, CV is defined as as it is equal to the number of US gallons, how many US gallons per minute, when the differential pressure or the pressure difference across the valve is equal to 1 psi. Okay, then this is CV. So we have this relation, very important relation. Q is equal to CV times square root of delta B over SG. Again, delta B is the pressure difference. Delta B is the pressure difference. Okay, in BSI. And the CV, it is the correction factor or valve flow coefficient. We can say that this is valve flow coefficient. Okay, so we can use this equation. This is a very important equation, and when we deal with the CV and with this equation, the units is imperial units, not SI units. Okay, the previous equation, which is Q is equal to K square root of delta B, we use usually the SI units. But for this equation we use the imperial system or English units, system of units. And we have table 7.1 in the textbook that relate the CV values for different valve size in inches. So we have like we have this, we have the CV value, and we have the valve size. Okay, for example, one for quarter inch, this is in inches. This is 0.3, here 3, it is half inch. 14, this is 1 inch. This is 35, 1/2 inch. We have, for example, 55, it is 2 inch, and so on. This is the table 7.1. Table 7.1. Table 7.1. Okay. And this is very important table for usually to determine the correct size of the valve. Let's take an example, which is example 7.9. Okay, 7.9 example. Find the proper CV value for a valve that must pump 150 gallons of ethyl alcohol per minute. So Q is equal to 150 gallons, okay, per minute of ethyl, okay, alcohol. The material or the liquid here, ethyl alcohol, with a specific gravity. The specific gravity for ethyl alcohol is 0.8. You know, specific gravity of water is 1. This is for ethyl alcohol. Sg for water is equal to 1. Okay. So here we use the equation Q again to equal to CV times square root of delta B over Sg. Sg is the specific gravity. I forgot to mention this. Sg is the specific gravity. And for ethyl alcohol, it is 0.8. So in this case, we need to calculate CV. CV is equal to Q times, because we need CV, so we need Q times divided by this or we can say Q times Sg over delta B. Sg over delta B. Here it is delta B over Sg, here Sg over delta B, because we divide. Okay, so in this case, this one is equal to 150 gallons per minute, okay, times square root of Sg is 0.8, okay, and divided by the delta B, which is 50 psi. This is 50 psi. Okay, this is 50 psi. Then we have CV is equal to 18.97. Okay, and this is the number of gallons per minute, US gallons per minute, if the pressure is across the valve is 1 psi. Okay, but the pressure here is 50 psi and the flow is 150. So only we have CV in this case 18.97 US gallons per minute. Okay. If we go to the table in 7.1, table 7.1, we have 14 if the CV is equal to this is valve size inches. For 14, if the CV is 14, then this is 1 inch in diameter. If it is 35, then this one is 1/2 inch. So now our CV here is 18.9. So here, so usually we select the larger value. So we select this one. So the correct size or the proper size for the control valve, we need to choose it as a valve with 1/2 inch diameter, which is equal to 3.8 centimeter. We need to select a valve with a diameter of 3.8 centimeter or 1/2 inch. 1/2 inch to have these quantities. Okay, then we will stop at this point. Thank you very much.